So the idea that we're going to start with is based in Chapter 2, which is the idea of a limit. I'll post this too, just in case you want to get a sense of what Chapter 2 is. But these are the sections we're covering in Chapter 2. We're starting off with the idea of a limit in 2.1, and that's more of a, let's just say that's a numerical introduction into the notion of a limit. 2.1, we'll look at numerics. 2.2, we look at the preliminary definition of a limit. It's more of kind of like a working definition of a limit. Again, in 2.2, we'll also look at some numerics and the graphs. Looking at numerical evidence and graphical visual evidence to determine limits. And then from there, in 2.3, we actually will develop sort of the algebraic techniques to compute limits. So 2.3 starts becoming much more algebraic. Typically, we refer to those types of procedures as analytic, where we're analyzing it by hand through, simplifying algebraic functions or trig functions or whatever. In 2.4, we look at infinite limits, and 2.5 is limits at infinity. So they're somewhat related in the sense that we have infinity starting to show up in our limits. But 2.4 and 2.5, they sort of solidify concepts that you've already seen before, namely 2.4 with infinite limits. We're able to, with the language of limits, redefine what it means to have a vertical asymptote somewhere. So these are vertical asymptotes, more or less. And in 2.5, limits at infinity. You think about when we looked at like polynomials in algebra or pre-calc, where we said what's the end behavior, what's happening way out here on this end, and what's happening way out here on this end. Do y'all remember doing that? So we're going to recast that in the sense of what's this limit way out here at infinity, and what's this limit way out here at infinity. So what those are going to describe for us are horizontal asymptotes. Probably up to this point, you might remember one function that had two horizontal asymptotes, but generally the functions we've worked with up to this point, they were like polynomials didn't have horizontal asymptotes, and then we looked at those rational functions which did have a horizontal asymptote. Either it had none or it had one, right? Those slant asymptotes. Do y'all remember those? But there are instances of functions that have more than one horizontal asymptote. One, hopefully, that you should know is sort of a trig function. Does anybody remember a function that has two horizontal asymptotes? Yeah.
Tangent.
Close. Well, yeah, I guess. Well, not the tangent. Close. Colder. Sine and cosine don't have any horizontal asymptotes. They technically are bounded by 1 and -1, but it's not something that they flatten out towards.
Arctangent?
Yeah, inverse tangent. You remember inverse tangent? So inverse tangent has these two horizontal asymptotes. There's other types of functions that have more than one horizontal asymptote, but so it looks something like that. So the idea in like 2.4 and 2.5 sort of It's helpful if you remember the processes of finding those kinds of asymptotes, but more or less in 2.4 and 2.5, we're going to say it's okay if you forget it, because now we have a calculus-based method to determine where those things are. 2.6 is continuity. Really, I don't have a lot to say about that right now, but continuity, you've seen different types of discontinuities before. So we've seen like holes in graphs. We've seen jumps in graphs, and even vertical asymptotes are discontinuities. So really in 2.6 we're addressing formally, informally in past math classes we said it's continuous as long as we can draw the graph without having to pick up our pencil, right? Well, we'll sort of motivate that section with a graph. It's impossible to tell whether we have to lift our pencil up or not. So we formalize the notion of continuity, again, in the sense of a limit. And then in 2.7 is the formal, yes, traditional mathematical definition of a limit. Usually people call those epsilon delta, so epsilon delta definition of limits. It has a tendency to get super analytical and super difficult. Fortunately, we're only, in 2.7, we're only going to focus on sort of this graphical interpretation of the definition. But chapter 2 is all about limits. And so, just to give you an idea of what calculus is, I would say more or less you can think of calculus as taking like algebra and trig and other stuff and taking the idea of a limit and just sort of dropping it into that. So when we take this notion of a limit and throw it into algebra, trig, we get calculus out of that. Calculus, just kind of historically, the Latin word translates to, or its root Latin word translates to pebbles. Based on the sense of, back in ancient times how they used to calculate stuff. So they were calculating things with stones, with pebbles. And so when you hear have y'all heard of like the triangular numbers and the square numbers and the pentagonal numbers? Have y'all heard of those? The square numbers probably for sure, right? Well, I think it does make a lot of sense if you kind of envision yourself back in those times, like counting things out with pebbles. Instead of representing 4 with pebbles like arranged that way, maybe it makes more sense to look at 4 like this, and we see that square formed, right? Or with 9, we see that square formed, right? It's the same thing with like the triangular numbers. 1 is a triangular number, 3 is a triangular number, 6 is a triangular number. So all of that stuff I think starts to make at least visual sense when we imagine those are stones sitting there. But anyhow, means a totally different thing to us at this point. So sort of my crummy diagram here. Calculus is really studied in sort of 2 parts. There's sort of 2 main pillars to calculus. We get really familiar with one and somewhat familiar with the other in Calc 1. So the 2 pillars sort of supporting that are the idea of derivatives or differentiation and integration is the other one. This we don't see this until later in chapter 5. It's the last chapter we look at. Differentiation, however, is what we're spending most of our time with. So that's chapter 3 and 4. Just as we go forward, what we're talking about here with differentiation with derivatives is we're talking specifically about an instantaneous rate of change. So really we could list a whole ton of things we could apply to that. So anytime you look down at your speedometer, that's measuring your instantaneous rate of change. Really anything you model in the real world, you can also measure its rate of change at a particular instant. So, we could list, thousands of applications. Rate of blood loss, the rate of water flow, the rate of heat flow, temperature change, whatever. And integration it's, I guess, a little bit more versatile in the sense that it applies to a lot of things, like, we'll just list a few. Area under a curve, work, force, pressure, surface area, volume, so on and so on and so on. If you go on to Calc 2 is, a lot of Calc 2 is devoted to studying integration techniques and stuff. Okay, so those are the main branches of calculus, and what's supporting both of those is the idea of a limit. So really, without the notion of a limit, you don't have a derivative and you don't have an integral. So that's why we are studying limits first, and then going on into chapter 3 and 4. The definition of the derivative and the definition of an integral both rely on a limit. They both have limits in their definitions. Okay. So that's kind of the bigger picture of what we're looking at. Do y'all have any questions? Those will be posted, so if you didn't get all that, it's fine. I don't have a handout for this. It's really just a short introduction to what a limit is and how it behaves. A couple of things we should, preliminary things we should mention. Do you all remember the average rate of change? I'll abbreviate that average rate of change. Who remembers that?
Distance over time.
Okay, yes, we could look at a specific example where it would be the distance over time. Specifically, though, it's not just like a distance over time. It's a slope, right? Which measures what? Something over something, but particularly what?
X over Y.
Y over X, but it's not just a Y value over an X value. It's actually a difference or a change. So it'd be like the change in distance over the change in time. Right. But the average rate of change is nothing more than the slope. So when we measure an average rate of change, this thing, rate of change, is just a placeholder for whatever you're measuring, right? We can measure an average velocity, we can measure average acceleration, average speed, right? So that rate of change is more of a sort of ubiquitous placeholder for whatever it is we're measuring. But the point is that when we measure an average change in something, that we're calculating the slope between 2 points on that curve. So if I had like this curve here, that's purple. You can't see it. And this point here, if I were to calculate the slope of that line there, then all it's doing is it's telling me on average from start to finish, what was that rate of change? What was the velocity? What was the speed? What was the acceleration? What was the temperature? Whatever it is. So that's our average rate of change. We'll just use M for slope. That's sort of a physical interpretation of what slope is. We look at, when we start looking at limits, and especially derivatives, we start looking at both a physical interpretation and sort of this more straightforward mathematical interpretation. So the sort of analog of average rate of change in a physical context to a mathematical context is what we're going to refer to as a secant line. So the slope of the secant line is the same thing as the average rate of change. So don't confuse the word. That secant here in this context has nothing to do with the trig function. Okay. Secant Latin word is, I can't pronounce it, but it's S-E-C-A-R-E. It's a Latin word, and what that means is to cut. So we have a line that cuts a curve, as we see up there. We call that the secant line. Okay, so we've got a mathematical interpretation as the slope of a secant line, a physical interpretation as average rate of change. So, you know, if looking back and we said we've got these 2 points, how do you find the slope between the 2 points? Well, it's the change in y over the change in x. But what we're working towards is, what if I have a curve? So we'll call this number 2. What if I had this curve and I wanted to measure the slope at a single point? So what's the slope of that line? How do we measure it? So given 1 point, how do you construct a slope? And this is going to refer us back to the instantaneous rate of change. basically, for now, we can think of it as such, slope at one point on a curve or a function. Again, that's a physical interpretation. The mathematical interpretation is the slope of a tangent line. Again, tangent there in that context is not the tangent trig function. Tangent, Latin word, T-A-N-G-E-R-E, I believe. Latin word that means to touch. So it's a line that touches the curve at a single point. And so those two things are really the basis of this section. We start with average rate of change or slopes of secant lines because we've seen those before. And then we look at how we take a notion that we already know how to work with and modify that so that we end up in this realm here with the instantaneous rate of change, or the slope of a tangent line. Do y'all have any questions at this point? All right. If you have calculators, I would get them out. We're going to do one example from 2-1, computing average rates of change. Give me a calculator. Okay. Just trying to make some space here. Just want to remind ourselves the average rate of change. So let's just state it a little bit more formally. The average rate of change of f of x on some interval, let's call it AB, is what? How we define the average rate of change? Right. So remember, it's just the change in the function value, f of b minus f of a, change in the y value over the change in x. So again, we're going to refer to that, depending on the context, we're going to refer to that as the average rate of change. Or we could refer to that as the slope of the secant line. So we'll denote the slope of the secant as m subsecant. just a really quick sort of trivial example. So it takes me 40 minutes to get to work, which is 20 miles. What is my average? We'll fill in the rate of change part in a second. What rate of change, though, are we measuring? A velocity, right? So we have time. And a distance, miles. So if you remember, when we measure any kind of slope, we're always just taking the change in y over the change in x. So when we measure this slope, we have the change in miles over the change in minutes, or miles per minute, right? Which is a speed. More specifically, it's a velocity because I'm traveling in a particular direction. But we can think about this as average speed or average velocity is what we're measuring. Miles per minute. That's our velocity. So I don't know what my commute looks like, right? When I'm backing out of the driveway, I'm going very slowly. In my additions, I'm going slowly. Then I get on the interstate or what have you, I'm speeding up, right? So we would expect that to vary depending on where I'm at. And then maybe I reach school here. It's like 20 miles away. So maybe it looks something like that. Maybe it looks totally different, right? The fact of the matter is if we're just computing the average, we don't care. Because to compute the average, we're going to say, okay, well, where did I start? And where did I finish? And then I'm going to measure that, the slope of that line. So that's my average rate of change, or slope of secant line. So what's the average, what is my average velocity? I've got the 2 points, 0, 0, that's where I started. 20 miles, I've gone in the 40 minutes. Right? Average rate of change, or the slope of the secant line. Change in y. 20 minus 0, measured in miles. And the change in x, 40 minus 0 in minutes. Put it down here. So I travel 1 mile in 2 minutes. Or if we want to do miles per hour, convert that to miles per hour. But again, all that's saying is, on average, from the time I leave my house to the time I arrive at school, right, I travel 1 mile every 2 minutes. Even though, on the interstate, like here, my velocity is a lot more than 1 mile every 2 minutes. So then, the question that shows up here in 2.1 is, at any particular time, let's say 21.37 minutes into my trip, how fast was I going at that moment? So then I say, well, I need to then measure the slope of this line right here. That's going to give me the speed that was on my speedometer at that particular moment in time. And so then that's where that instantaneous stuff comes in. So here we'll just say on average. I travel 1 mile, 1 mile in 2 minutes. Is that 30 miles per hour? But again, at any given time during my commute, my speedometer probably wouldn't say 30 miles an hour. So let's look at a particular example related to this, and then we'll start looking at how the slope of this tangent line, or the instantaneous rate of change, comes out of looking at the average rate of change. Everybody have that? So we have a position function. S of t, which is negative 16t squared plus 96t. Position is measured in feet, and t, time, is measured in seconds. We'll do 3 of these. So let's find or compute the average velocity over the given time intervals. First interval, let's look from 1 to 2. Just remind you that when we're computing this average velocity, that is our average rate of change. That's the same thing as computing the slope of a secant line. The slope of a line connecting 2 points. And just be careful, the problem tells you that what you're given here is a time interval. So this is just some interval along the x-axis. So I'm gonna capital V with this AVG for average velocity. So again, we need to measure the change in the function. So that's position at time 2 minus the position function at time 1 all over 2 minus 1. So I'll take a moment, hopefully more than a couple of us can calculate this and verify. Negative 60. Just to write the first one out, that's what we're computing. If you get something, let me know if you want. Anybody get anything yet?
58 per second.
58? Anybody else get 58? Just kidding. Okay. What did you get? 48. How about 48? How about 48? So 2 for 48, 3 for 48. Is 3 good enough? Are we convinced? 4? 4 people, 48. 5. All right. 48. All right, recall our units, change in Y, feet, and time was measured in seconds. So during the first, time equals 1 second to time equals 2 seconds. On average, this thing was traveling 48 feet per second. All right, a different time interval. Let's look at the time from 1 to 1.5. A lot of calculators have like storing options depending on what one you're using. It's worthwhile investigating how to do that so these problems don't become tedious. There's a handful of them in your homework, and there's going to be one on your exam similar to this where you're computing these kinds of things. It shouldn't be terribly difficult, but it's really tedious to just, especially if your calculator doesn't store stuff, you've got to enter all of that stuff over again. So try to find out if you can, whatever calculator you're using, try to maximize this process. 56 feet per second.
Correct.
Anybody else get 56? Should get 56. Hopefully y'all are okay with the computations. I don't know if you're not getting it, it might be something to do with how your calculator does the order of operations. Some calculators need parentheses around things, some don't. But I assume that we're okay with the computation. It's pretty straightforward. Does anybody have any issues with what we're doing? Any questions? Okay. And let's look at one more time interval. And then we'll look at a table. So let's go from 1 second to 1.1 seconds.
About 62.4.
62.4. Anybody else confirm? No. Okay, so I'll put the rest in there. So we get the idea of the computations. Here's the rest of the table. We did the first three, they're going to do the next three. And really what we're looking at is this average velocity here in the second column. This is the slope of our secant line, however you want to view that. What we're looking at is the time interval is getting smaller and smaller, right? From 1 to 2, from 1 to 1.5 to 1.1, etc. Right, we're getting closer to 1 in the sense of the time interval. And does it look like the average velocity is approaching a specific unique number? Yeah, what does it look like this would continue on to? So it looks like our average velocity is getting closer to a particular value at 64 feet per second as the time interval gets smaller and smaller, right? What's illustrated here in terms of this numeric evidence is that idea of a limit. So what we're doing here on the time axis, we're fixing this point at 1, and we're calculating this slope. And then we're calculating this slope, and then we're calculating this slope. And we're seeing that each time we calculate those slopes, the average rate of change over smaller and smaller intervals t values or x values or whatever they may be. In this instance, we're seeing the y values or the output approach a specific number. So let's write that down and we'll make it a little bit more formal. So let's just say over smaller and smaller intervals, time intervals, the slope of the secant line, or the average velocity, average rate of change, slope of the secant line, they're one and the same. Just say gets closer and closer. To a specific number. Which is the instantaneous velocity, or the slope of the tangent line. So if we take, if we compute average rates of change over smaller and smaller intervals, eventually reaching some fixed point, then you're coming up with the instantaneous rate of change, or the slope of the tangent line. All right. So here's what's happening visually. The average rate of change is in green. That's what we're measuring, just change in y over the change in x. Over the time interval from 1 to 2.05 seconds, we measure that average rate of change. And then we say, okay, we'll make that interval a little bit smaller, compute again the average rate of change, interval smaller, compute the average rate of change, so forth and so forth. And we see that average rate of change, the green line, then merges with the instantaneous rate of change, which is the red line. So over smaller and smaller x values or intervals, that's what we're doing. We're fixing this point and we're computing the slopes between these two. And eventually this point gets super, super close to this point where we can't tell the difference anymore. And then we have the slope at a certain point. Does that make sense? None of that happens without a limit. So this idea that we have not made precise at all, we've just sort of stated it. So that idea over smaller and smaller time intervals, that's really the idea of a limit. I think when most of us think about maybe when you think about a limit, you think about perhaps a limit that's way out here, right? It's unreachable, it's out at infinity. But really there's more than one type of infinity instead of just going on forever. Just in the sense of the properties of real numbers, how many numbers are in between 0 and 1? There's infinitely many numbers between 0 and 1, right? So if I said, hey, here's a point along this number line, how close can I get to that point? How close could I get to that point without touching it? Could I get here? or here, or here, or here, or here, or here, or there. I can get infinitely close to that single point or that single value without ever having to touch it, right? So take the x value or the t value equal to 1, right? I can just keep adding zeros in here, and I'll never actually be at 1, but I'll be infinitesimally close to 1, right? So that's the idea of a limit, is I can get as close to something as I like without ever having to touch it. I mean, really, physically, it's kind of a paradox, maybe not in like a quantum sense or something, but you know, how close can I get to this board without touching it? Eventually, I feel the sensation of me touching it, right? But the idea of real numbers, that's one of their properties. I can get as close as I like to something. As I get as close as I like to something, in terms of the independent variable, what is my dependent variable doing? Does it appear to be approaching a solid single number? So that's the idea of a limit. Again, we don't really formalize that here. We formalize it in 2.2, but let's go ahead and write this stuff down. We have observed a couple of things. The instantaneous velocity at t equals to 1. Remember, the instantaneous velocity is just because that's relevant to our example, but in general, this will be an instantaneous whatever. So instantaneous acceleration, instantaneous temperature, whatever change or whatever that is. But that's also the slope of the tangent line. So we've observed that the instantaneous rate of change or the slope of the tangent line here at t equals to 1 is computed or was computed by taking the average rate of change. So we'll write this in a couple of ways. The average, which is also mathematically the slope of the secant line. So that was our sort of starting point, but then what we had to do was we had to allow all of the other times to get closer and closer to t equals to 1. So our notation for that is we're going to write LIM for limit, and we're allowing the t values to get closer and closer to 1. So it's LIM and then t with the little arrow indicating that t is approaching 1. And we did the same thing with the secant line because it was just a different vocabulary for the same thing. So once we've done that, that's how we got our instantaneous, or the slope of our tangent line. And honestly, computing limits like this is super tedious. You've got a few of them in your homework, and you're going to be sick of it by the time you're done. Fortunately, that's where the rest of the chapter comes in. Sort of expedites the entire process. But that's the basic idea of a limit. Do you all feel comfortable with that? It's pretty straightforward. Are there any questions on that conceptually or anything? Well, that's the basic idea. I will mention, though, that in your homework, they have you compute the average velocity over a more generic interval from 1 to 1 plus h. So this, I think, maybe makes sense when we think about the last three computations that we looked at. We went from 1 to 2, and then from 1 to 1.5, and 1 to 1.1. So why on earth would we compute the change from 1 to 1 plus h? What would that do for us?
You could make it so that the limit as h approaches 0, when you compute the limit of the average velocity over a larger stretch, you can make h go to 0, and that makes it as close as possible without actually having to pick a t value or something.
Right, yeah, exactly. So what this is allowing us to do is notice this is what we're computing anyways. This is from 1 to 2. If I go from 1 to 2, what's 1 plus h? Or what's h, rather? It's 1, right? So here, h equals 1. Here, h equals to 1/2. And here, h equals to 1/10. Right? So it's just another way to view all of those computations. And think about it, if you had to do like 6 or 7 or 10 of these, it's honestly easier to do it this way, where we're just saying, well, each time I'm just changing from my left endpoint, which is fixed at 1, by a specific number. So if I compute the average rate of change over the interval from 1 to 1 plus h, let's go down here with that. So what's going to come out of this here, the denominator, we're just dividing through by h. This is s of 1 plus h minus s of 1. So what do we get out of this when we compute this? It's what? It's a simplicity. Yeah, namely, I'm just looking for that when we compute this, we're getting not a function of t or a number anymore, but we're going to get a function of h. So that's what we'll just write here. This outputs a function of h. Once we get that function of h, that is the average velocity for any step away from 1. So I've got this function of h. If I want to measure the average velocity on this interval, then I just plug in h equals 1 into that function. I have my average rate of change. From this interval, plug in h equals to 1/2. This interval, h equals to 0.1, and out comes those same numbers that we computed. Does that make sense? So it's a more generic way to look at it, which is often helpful, especially when we start looking at the definition of a derivative. How do we actually define the slope of the tangent line? So just, again, I just want to solidify this. Let's say let's say that we computed this average velocity to be equal to, I don't know, 60 plus 10h. Once we computed all of this is what we ended up with. Then once you have this, no matter what time interval you're given, you can then just plug in the step away from 1 or 5 or wherever it is into that function to measure it. So let's say this is on 3 to 3 plus h. And then we said compute the average velocity on the given intervals. The 3 to 4. 3 to 3.5. 3 to 3.1. 3 to 3.0001, etc., etc. So what we started off with, we just started throwing these numbers into a function, right, and just measuring the specific change for this one, and then for this one, and then for this one, and then for this one. Here with this, we would come up with this function of h first, computed this way. Ours would be a 3 plus h, but it doesn't matter. Once we have this function of h, then we can just throw these step sizes in here. So here, h equals 1. Plug that in there, then we'll have the average velocity on that interval. H equals to 1/2. We'll throw that into here, have the average velocity on that interval, etc., etc. Is everybody okay with that? So I don't know that that's completely necessary, but it is helpful to have a couple of ways to look at certain things. Okay. Do you have any questions? So that's the end of 2.1. We'll start 2.2 on Thursday. Let me know if you have any issues with my math lab. Just send me an email.